Hello there, and in this video we're going to introduce an algorithm that can be used to find all of the prime numbers that are less than or equal to some number of interest. In this video we're going to be choosing the number 100 to sort of demonstrate this algorithm. And this algorithm is known as the Sieve of Eratosthenes. Eratosthenes. Right? Definitely, I guess, a complicated name to pronounce. But we're going to just be focusing on how this algorithm sort of works and sort of discuss a couple of things in terms of how efficient it is and how quick it is in finding the prime numbers in a certain interval of interest. Alright, so as I said, the Sieve of Eratosthenes is a method that is used to find all of the prime numbers in a certain interval. So definitely the first thing that we need to do is define what a prime number is. And a prime number is an integer or a positive integer. So it's a positive integer, so an integer greater than 0, that has two distinct or different divisors, 1 and itself. So based on this definition, it's very easy to see that 1 is not a prime number. And 1 is not a prime number because it does not have two distinct divisors. The only divisor 1 has is 1, and that is it. There is no other divisor in it. But the number 2 is a prime number because it has two distinct divisors, 1 and itself, which is 2, right? 1 divides 2, 2 divides 2, but 3 does not go into 2 evenly. So 2 only has two distinct divisors, right? And it's also very easy to verify the following theorem, that 2 is the only even prime number, right? Because we can take, for example, 4. 4 is not a prime number because it has more than two distinct divisors. It's divisible by 1, it's divisible by itself, 4, and it's also divisible by 2, right? So every even number is divisible by 1, 2, and itself, provided that that even number is larger than 2, right? So 2 is clearly the only even integer, right? So we can easily see that all the multiples of 2 are not going to be even. So we already crossed out 4, so we can also cross out 6, 8, and 10. And we can pretty much cross out these entire columns that are associated to multiples of 2. So all the multiples of 2 in column 2, all the multiples of 2 in column 4, column 6, column 8, and column 10, right? So I'm just going to quickly go through them and cancel them out. Alright, so we've pretty much gone through and crossed out all of the multiples of 2. So we have all of the multiples of 2 greater than or equal to 2, and we've also crossed out 1 because 1 is the smallest integer, positive integer that is not a prime number. So just crossing off all the multiples of 2, we've pretty much made the sample space of the set of numbers that we're looking at, namely 1 to 100, we pretty much halved the entire interval, right? So that's definitely a great start. So now we're going to move up to the next integer that is not crossed out, right? So the next integer in sequence is going to be the number 3. So 3 is definitely a prime number because it only has two distinct divisors, 1 and itself 3. It's not divisible by 2, and it's not going to be divisible by any integer greater than or equal to it, right? So 3 is a prime number, so it's the second prime number in sequence, and all multiples of 3 will not be a prime number, right? Because, for example, the next multiple of 3 will be, of course, 6, and 6 is divisible by more than two numbers. 1 itself, 6, and also 3 because it is a multiple of 3. It's also a multiple of 2, but we're just going to focus on 3 for the time being, right? So 6 is not going to work. Also 9 is not going to work as well, right? So the next multiple of 3 is going to be 12, but we've already crossed that out. And the next multiple of 3 is going to be 15. and then 18, then 21, then 24, and then 27, and then 30, and so on, right? Now, if you sort of look at this diagram, you should see that there is a pattern and structure, right? So if you, because these yellow X's almost make diagonals, so you can pretty much see that 33 is going to cross out, 42 is going to cross out, and 51 is going to cross out, right? The next diagonal is the one that contains 9, 18, and 27, so those are the multiples of 9, right? So we're going to cross out 36, we're going to cross out 45, 54, 63, 72, 81. Of course, if you're writing a C++ program or a MATLAB program, it's just going to march through the integers 1 through 100 and just cancel out all the multiples of 3 directly. But in this tabular approach, you can clearly see that there is some structure associated with the multiples of 3 more over the multiples of 9, right? And we're going to talk about this relation a little bit later when we start talking about congruences in a little bit more detail, right? So I'm just going to go through this table and just cancel out all the multiples of 3 that I have here. Alright, so now that we've crossed out all the multiples of 3, now we're going to move up to the next integer that we haven't canceled out, and that's going to be the number 5. So of course, 5 is a prime number. It's only divisible by 1 in itself. 5 is not divisible by 2 since it's not even. It's not divisible by 3. It's not divisible by 4, and it can't be divisible by all numbers greater than or equal to it, right? So 5 and all of the multiples of 5 will not be prime, and that of course is easily provable. So we can easily cross out all the multiples of 5. We can just march down this center column and cross out 25, 35, 55, 65, 85, and 95. Now, of course, we've already crossed out all the multiples of 2, so all numbers that are ending in 0, which are the other multiples of 5, we've already canceled out. So this part of the algorithm actually has not given us much, but it has made our set a little bit more smaller. So the next number that we're going to be looking at is, of course, the number 7. So 7 is a prime number. That's easy to verify. So the next number will be 14, but that's already canceled out. So let's see if we can find a pattern here. So 14 is here. 21 is going to be here. So the next number is going to be 28. And then what's after 28? So 7, 4, so then it's going to be 35, right? So 7, 5. 7, 6 is 42. 7, 7 is 49, and so on. So if you sort of look at this table before we start to cross things out in the more brute force method, notice that these blue X's actually make a nice little L pattern, right? So this is a very, very beautiful pattern in terms of this table because, the multiples of 7s are sometimes harder to forget, right? So if we sort of go down an L, of course, 70 is going to be canceled out here. If we move down an L from this point, this is going to be canceled out here. And if we sort of go down here, that's going to cancel out 77. And we can sort of continue this process forever, right? So if we sort of move down an L from this position, that's going to cancel out that. That's going to cancel out that, and so on. So the multiples of 7 are very, very easy to spot, at least in this pattern. So we've crossed out all the multiples of 7, so now we move up to the next integer that is not crossed out, right? So how do we know that the next integer not crossed out, provided that we have canceled out all of the multiples of the preceding prime number, that this number is indeed prime, right? So how can we sort of verify this identity? So why is 11 prime? So if 11 is prime, it's only divisible by 1 in itself, namely 1 and 11. And it cannot be divisible by any number strictly greater than it, right? So it must be divisible by 10, 9, 8, 7, 6, 5, 4, 3, and or 2 in order to qualify as not being prime, right? Now, if it was divisible by one of those numbers, that means it would be a multiple of that, right? So that's an important characteristic of divisibility, right? So if x is divisible by y, so that means we're looking at something like 12 divided by 4, because 4 clearly does divide it into 12 evenly, then x is a multiple of y, right? right? Because if 4 divides into 12 evenly, that means this is some integer k, right? So if that is true, then that means 12 is equal to 4k. So clearly 12 is a multiple of 4, provided that k is a positive integer, right? And of course it can be negative, but we're just focusing on the positive case here, right? So using this principle, you can prove that this method is going to force that the next number that is not canceled is going to be prime by default, right? Which is very powerful. So all the multiples of 11 will not, of course, be prime because they're going to be divisible by 1, 11, and itself. So 22, which is even, 33, which is divisible by 3, and all of those, I believe we have canceled all of them. So we haven't really achieved anything here. So the next thing that we need to look at is, of course, 13. So of course we can continue this process as long as we want, and we're going to realize that 17 is a prime number, 19, 29, 23, 31, 41, 43, 37, 47. These are all going to be prime numbers, right? Now, are we going to be crossing any of these numbers out past this point, right? So if we look at 61, so 61 you can verify that to be a prime number 2 by the same exact process. So how do we know that all of these others are not going to be multiples of 61? So the next multiple of 61 is going to be twice that, so 122, which is larger than 100, right? So if that's the case, then 61 is going to be prime, and all of these numbers here are going to be prime as well using the same exact logic, right? So in a way, you only need to look up to half of the upper bound of the interval that you're actually looking. So if we sort of go up to the number 50, right? So the next number is 51, so the next multiple of 51 is going to be 102, which is larger than 100. So since that is the case, all of the numbers after it are not going to be multiples of 51, therefore we're not going to be canceling any of those out, right? So we actually only need to look at, in this case, n over 2, which is 100 divided by 2, which in this case is 50. So that's going to be the upper bound for which we're going to have multiples that sort of delete in this algorithm, right? So of course this is a method for finding the prime numbers in between 1 and some upper bound n, which again is called the Sieve of Eratosthenes, right? Now, of course, I'm not going to get into the numerical analysis of how quick it is and what are some other better methods, but you may be able to find that, okay, we only need to look up to n over 2, right? So that definitely can make this method a little bit more robust, right? Now there is actually another number that you can go up to, but we're going to leave that to another video to just sort of discuss because sometimes this property is not so obvious. So we'll wait until then to discuss that improvement to this algorithm. So I hope you enjoyed this method on finding the prime numbers in a certain interval. Hope you enjoyed.